Okay, so with all of this, I can plug that stuff into my program. So we're back here. So I've already coded that up in hopefully the same order. And I will go through, check, I've got 23 equations, 23 variables, I can solve it. And I see that I've got all my view factors. So good, so this is like step one, right? This is get all the view factors for all the surfaces involved, and then we can make an evaluation of the radiation exchange between them. Any questions on this? Okay. All right. So let's see, we want to evaluate radiation exchange. So the way to do this would be, I'm going to provide an energy balance on each node. If I go to do this, I'm going to uncomment this code. I'm saying the Q dot I, that is the heat flow that's going through surface I being 1 through 4 in this case, is equal to the area of I times Stefan Boltzmann constant times the sum of all these view factors times the temperatures of the surfaces. So if I try to solve this, I guess I'm going to see that I don't have enough equations. I'm 4 short. And maybe it's obvious, but that's because we didn't actually specify the boundary conditions yet. But the point I want to make is that when you're doing this energy balance and you go through it, you have to, for every single equation, you have to tell the program something. Like you have to tell it a temperature of the surface, or you have to tell it the heat flow, or if you happen to know well, it'd be radiosity later, but the emissive power, as far as we've talked about, if you happen to know the emissive power, right, you can substitute that in for the temperature. You have to give it something, otherwise it just doesn't have enough information. So for these, we just enter in the boundary conditions that I told you at the beginning. We had 3 specified temperatures and 1 specified heat flux. And of course, Ease is going to be now happy to solve this, but let's make sure. So, all right, we have the right number of equations and variables, and we can solve the problem. And then we end up with heat flows. So some surfaces are gaining energy, some surfaces are losing energy, and one surface, which we've told it to be 0, is doing nothing. It's just finding the right temperature to make sure that condition is true. All right. So that, I mean, it's pretty straightforward, right? You're just entering the energy balance equations and telling it a boundary condition. We've kind of contained this whole problem to what's going on inside the geometry, though. If we want to somehow relate these surface temperatures to stuff that's going on outside the geometry, you might need to introduce some other kind of boundary condition. And that might be something like, let's say that the surface, which one did we pick here? Surface 4, okay, they called it a shield. So that's why it's S. So surface 4 is our shield. We said initially it's 300. Actually, let's solve for that, assuming it's this really thin little piece of metal and it's sort of negligibly thin. We would say then that the temperature of that body, both internally and externally, is a single temperature. But let's solve for that temperature. So let's say that instead of specifying it, let's give it some convection condition with the surroundings. So I'm going to comment this out here. I'm going to add a new condition here. Let's see if this works. So I'm adding a new condition. What I'm saying is I'm going to say T infinity, that's the surroundings temperature is 300 now. And I've got some convection relationship, T infinity to T4. And we have to relate it to the heat transfer across that surface. So that's our balance on surface 4. So we can solve that, and then now we would see our temperature, which was previously like what was it, 270 something. It's changed, right? And some of the other heat flows have changed as well. So we're solving this like kind of coupled problem, which makes it a little more practical. So one thing I want to make clear about this is when we're talking about the radiation exchange from surfaces, and we talk about the Q dots here, like this Q dot. This Q dot is the thing that's going across the surface into the body on what's on the other side. So all the other stuff that we've talked about with conduction, like that still would apply. Like you could relate the radiation at the surface to conduction through the body using this heat transfer. And it's, again, kind of an obvious thing, but it trips people up. Like somehow you think you're moving to radiation and none of this applies anymore. So it's all still the same. It's just that space in between other surfaces is really what we're concerning ourselves with here. Okay, so that's the example. Questions on that?
To rephrase what you just said, so if I understand it correctly, you're saying that the radiation from two bodies is that amount of heat transfer, and then it would go into conduction.
Yeah, like this is saying that if I looked at these surfaces back here, we've just computed the radiation, we've computed the view factors, we've specified temperatures and such. We have now computed what is the heat flux across the surface, or heat flow across the surface. So like in this example, I'm saying for 3, I've got some flow that's going across 3, and then it's exchanging with all these other surfaces out here. This Q dot here, right, if I were to say that's my Q dot 3, Q dot 3, if it turned out this was like mounted, let me clear this up a little bit. If it turned out that this was mounted to some, piston or something like that, and you wanted to look at conduction, that Q dot, in here you'd say, Q dot is equal to minus K AC dt dx, right? It's still the same. The heat transfer is heat transfer. It's just that we're computing what's going across the surface. So it's essentially a surface energy balance. All the other stuff still applies on the other internal side of the surface. Other questions? Yeah, so we were assuming that if there was radiation, it was essentially between two surfaces usually. Like, so you'd say there's a surroundings and there's a surface. And the exchange would be T to the fourth, the difference of temperature is T to the fourth. And then we could approximate that, that resistance between those two bodies using that T bar, or was it 4 T bar cubed? You could do that. That's still valid here, but what we're doing is we're introducing multiple surfaces. So before we said radiation exchange is happening, but the view factor is 1. So there's always, any radiation that leaves goes from 1 to 2 and vice versa. Now we're making it more nuanced, and to say that you can have a fraction that's leaving that's going somewhere else, and you can have different temperatures involved of those. So it's still valid, but only in the situation where we have two surfaces, the view factors are 1. It would be the way that we wrote the energy. So if we look at the energy balance in E's back here. So the way I wrote the energy balance here would be T surface I to J. So this would be Q dot I from I to J. That would be leaving the surface. So if it's positive if it's leaving that surface. And if you looked at the results, we had some that were leaving and then some that were actually net gaining, which would be negative. Okay, so that's the example on that. That gives you maybe an idea how to go through view factor analysis and then apply it to a simple energy balance. We did it for 4 surfaces. You can scale it up and do it for however many you like. It just means you have to do more work in getting the view factors.